have some mass that Alice and Bob are trying to move across a surface. It has some mass. So we have a rope with some tension being pulled by Alice to the right, and the rope is some angle theta above the horizontal. So Bob is pushing on the mass from behind, and he's pushing at some angle phi relative to the horizontal with some magnitude p. And the box is hard to move because it's sliding across the ground with some coefficient of friction mu. So this is the coefficient. Not right very well, but coefficient of friction across the ground. And so we want to know, one, what is the acceleration of this mass? And I'd also like to ask the question after that, is there some angle phi where Bob is not helping? So what does that mean? So to understand this, we're going to have to do a Newton's second law analysis of this system. So my first job is to choose an object, right? Choose one object. I think as the object, I'm going to choose the mass. Next, I need to find all the forces on this object. So what are the forces on this object? Well, gravity acts on this object, and so I'm going to give that a symbol. I'll call that F sub g. So that's gravity. Every other force has to be in contact with my object. So what things are in contact? Okay, there's a tension. The rope is in contact with the object. So there's going to be some force due to tension. That's T. So it's also in contact with the ground. So the ground is a contact force. And so we go back to our contact force model, and we ask our question of whether or not we want to divide our contact force model into the normal and the frictional force, normal perpendicular to the surface. And we know that this thing is sliding across the ground, and so friction is playing a large part of this problem. There isn't an obvious direction of the combined contact force. So it seems pretty clear that we'd like to divide our contact force between the ground and the mass into a normal and frictional component. So we have, we'll call the normal force, and this is, from the ground. And I'll call that N. And so there's also going to be a friction from the ground. So I'll call that F sub F, the force due to friction. Okay, what else is in contact? Well, there's also Bob here pushing on the mass. Well, that's also a contact force. So we can ask ourselves the same question. Is it worth splitting up Bob's contact force into a normal and frictional component? We certainly can. Every contact force can be divided in that way. But I don't really think so. I'm given in the problem that Bob is exerting a contact force on the mass with magnitude p. It's in a direction of phi below the horizontal axis. And so I think that I would just leave that as a contact force in its vector form without splitting it up into a normal and frictional component. I'm given a sort of a push force. It's sort of a p, so I'm just going to call it p vector. It identifies to me, it's the contact force of Bob pushing on the mass, and so it distinguishes it from my other forces. But it just has some magnitude and direction due to the contact of Bob pushing on the mass. All right, so that's step 2. I've chosen one object and I've found all the forces on that object using the ideas we used before. I isolate the object, there's gravity, and I find everything that's in contact with the object, and then I use my various models for my tension force and my contact forces to be able to set up what they are. All right, so the next step is to apply these forces into a free body diagram. So a free body diagram starts with a dot that indicates the particle model of my object. Now I need to put all of the forces and nothing else on the free body diagram in the direction that they act with their tail at the center. So let's do the obvious ones first. So I have a force due to gravity, and it's pointing down. And now the tension force, well, it's at some angle. All right, so that means I need to I need to establish a coordinate system here. A coordinate system has to be on every free body diagram. So I'm going to choose my coordinate system to be parallel and perpendicular to the ground. I'm going to call this direction positive x and that direction positive y. Now I can identify my tension force. My tension force, using my tension force model, has a magnitude that's T, and it is in the direction, along the direction of the rope at the point of contact with the mass, which is an angle theta above the horizontal axis. All right. My next is the normal component of the contact force with the ground on the mass. From my contact force model, it's perpendicular to the surface in the direction from the agent to the object. The agent is the ground, the object is the mass. Here's the surface, up is perpendicular, so that force points up, and it happens in my coordinate system along the positive y-axis. All right, so now the frictional component. Now the frictional component is tangential to the surface, so perpendicular to the normal, and it acts in a direction that's opposite to the motion of the object relative to the agent. Well, the object is moving to the right, and so the frictional force, which is parallel to the surface, is going to be in the opposite direction of that motion relative to the agent, which is the ground, which is in the negative x-axis. So the frictional force points in the negative x direction. Now last I have the push force. So I want to draw that on my free body diagram as well. Remember, vectors can be translated everywhere you want as long as you don't rotate them. And for a free body diagram, I always want my tail of my force at the point of my free body diagram. So my push force is going to look like this, with the tail at the center, and it has some angle phi relative to the horizontal. And if that's not entirely obvious, then you have to go back to your picture. Always have a very good picture. And so if I extend my push force this direction, I can see that this angle is the same angle phi as the one I had here, and so that tells me that this angle right here is phi as well. And so sometimes, like I have here, my picture's getting really complicated. If that's the case, then draw yourself a new picture so it's not so complicated. I have the push force coming in. And the push force exists along this line. I knew that this angle was phi, and so geometry told me this angle was phi. And so if you have a complicated problem, you just have to have lots of blank scratch paper to work on. So you can draw lots of pictures, new pictures, large pictures, so they don't get all crowded so you can't tell what's going on. So you can clearly identify all your angles and do your trigonometry properly. All right, I now have a free body diagram, part 3, done for this system. I have a coordinate system, all my vectors on my coordinate system. And so I can identify what they are and what direction they're going. All right. Now, the next task is to do the vector sum of these forces. Now, to do the vector sum is just a matter of applying our rules of trigonometry to find the projections of all the forces on the axes so we can come up with the components of the forces. And there are lots of ways to do this. So I will show you one way that I think is fairly transparent in order to keep all my vectors straight. So what I like to do is start with each vector, and I'm going to add them vertically. I'm going to start with the force due to gravity and write it in component form given my coordinate system. So my force due to gravity has no component along the x-axis, but it has its full magnitude along the negative y. From my gravitational force model, the magnitude of my gravitational force is the mass of the object times gravity. Now, it's along the y-axis, and then from my graph, I see that it points in the negative direction. Remember, my model just says it points towards the center of the Earth. I have to come up with my coordinate system to determine whether that's a positive or negative value. All right, so my next is my tension force. And so my tension force is not along an axis, so that means I have to find my components along the positive and along the x and y axis. Again, the way I do this is I always find components from my triangle, which are just lengths which always give me positive numbers. And then I always go to my coordinate system to see whether those numbers are positive, whether the components are positive or negative. If I want the x component, that is simply the length here of this green line. And the length of that green line is the magnitude of the tension force times cosine theta. It is along the x-axis, and given my coordinate system, that's positive. Now, if I want this green line, which I've identified here, this is the component along the y-axis that has the length. The length of that side of that triangle is the hypotenuse, which is the magnitude of the tension force, times sine theta. It's along the positive axis, and looking at my coordinate system, I see that it is in the positive y direction. So that gives me the tension force in component form. Now I go to the normal force of the ground on the mass. Well, the normal force has 0 component in the x direction, and it has its entire magnitude, which I identify with just n, in the y-hat direction, and it's positive. And so I just give it a positive sign there. Next is the friction in a component form. So it has its entire magnitude lying along the x-axis. From the contact force model, the magnitude of the frictional force is the coefficient of friction times the normal force. So that's the magnitude of the x component, since it lies entirely along the x-axis. So it's on the x-axis, so that's I. And then from my coordinate system, I see that it's pointing in the negative x direction. As long as you always assign your signs, positive or negative, from your picture in your coordinate system, from your free body diagram, then you know you'll never get them wrong. All right, so then, and it has 0 in the y-axis. And finally, I have this final contact force, sort of the push force that I just identified with a P. It's just another contact force. Now it has components along the X and the Y. So the first is have to do the same thing again. Now I'm interested in the X component of this push force, which is the hypotenuse, which is the magnitude of the push force, times cosine phi I hat, and looking at my coordinate system, that's just the length, the side of the triangle, that's in the positive x hat direction. And now I want to know the length of this green line. Well, using trigonometry, that's just p sine phi, where p is the magnitude. And these are magnitudes, so those are always positive numbers. So this is in the y hat direction, and now looking at my coordinate system, I see that this component is in the negative y direction, so I give it a negative there. So I find the components by looking at the magnitudes of the vectors and finding the lengths of these triangles, which are positive numbers, and then I assign the signs given my picture in the free body diagram. All right. So now, sort of setting it up in this way, there's a number of ways to do this, but I find this particularly transparent. Now, the next step, what we're working on right now, here is the vector sum of the forces. And the vector sum of the forces is set equal to the mass of the object times the acceleration of the object. Well, by writing my forces in this way, I now have an easy way to sum these forces. If I just sum these vertically, this plus this plus this, well, this plus all of these forces together is then equal to the mass of the object times the acceleration of the object, which is a vector. So if I write this in component form, it gives me the mass times the x component of the acceleration in the x direction plus the component of the acceleration in the y direction, which, from my picture, I know to be 0. The system isn't, well, from the statement of the problem. I was given in the initial problem when I talked about it, Alice and Bob are sliding this across the ground. So given that the original context of the problem said that it was sliding across the ground, then I know that it's not being lifted up and that the acceleration in the y-axis is going to be 0. So this is the vector sum of the forces on an object. Now this vector sum, which is equal to mass times acceleration, now gives us a way to establish relationships between the parameters of our problem which will help us solve. And so given how we know how to do vector arithmetic, we know that the sum of all the x components is equal to the x component of the result, and the sum of all the y components is equal to the y component of the result. So this is the way we translate our vector equation, which is this vector sum of all the forces is equal to the mass times the acceleration, into relationships between the parameters we can use. So do this one first, and we have t cosine theta minus mu times the normal force plus p cosine phi is equal to the mass times the acceleration. And I'm just going to leave the entire magnitude of the acceleration because we know it's entirely along the x-axis. So the y component give me another a relationship. It says that negative mg plus t sine theta plus n minus p sine phi is equal to 0. So, does this information give me enough to solve my problem? In the beginning, I was told that there's a tension T at angle theta, push P at angle phi. So these are, and a coefficient of friction mu. So these are knowns. And so let me stop here for a minute. Many people may be used to be given numbers. And so some students will look at that and say, well, I don't know what T and P are because it's just T and P. But in this case, the problem is assuming that we know those, but we're not given explicit numbers, but we want to solve for our unknowns in terms of the generic forms of those forces. So the problem says you know what the T and the P and the theta and the phi are, and the mu, the coefficient of friction, but they're not giving you explicit numbers for those. They want you to work the entire problem in terms of the variables. All right, so in this case, we're forced to do that. In general, you always want to solve your problems in terms of the variables first, and only put in numbers at the very end, unless you have some very compelling reason to do so. So if we look at this, we know our tension and our push force, theta and phi and mu. What we don't know are our normal force and the acceleration. So we have two unknowns, but we have two equations, so we should have enough to be able to solve for this expression. So there is no acceleration in the second equation. So I'm going to use the second equation to solve for n and substitute it into the first equation to be able to get the answer. So if I solve this second equation for n is equal to mg plus p sine phi minus t sine theta. So there I'm just solving that one for n. And there seem to be a lot of components to this problem, but really it's not so bad as long as you have a lot of space to work, so you don't get so your things don't get too crowded, and you can keep track of all your parameters. In fact, I'm going to move down here, and now I'm going to substitute this back into here. So this gives me, so I have t cosine of theta, and I'm just going to add my second term here, p cosine of phi, and so this is minus mu times n, which I have here, which is mg plus the push force sine of phi minus the tension sine of theta, and that whole combination is equal to the mass of the object times the acceleration. So now what am I going to do with this? What I'm going to do is I'm going to look at all my terms and sort of combine them together and see if the result makes sense. So I have, if I multiply this out, I'm going to combine my tension terms. So, well, let's multiply it out. Cos theta plus p cos phi. To be honest, you rarely lose time just completing all of your steps. Most students lose time by trying to skip steps, making mistakes, getting wrong answers, and then staring at the problem, wondering what went wrong. You rarely lose a lot of time just going through all the steps clearly so that you make sure that you don't make any algebraic errors. So I'm going to check. There's negative, negative. This should be a positive, right? Negative times a negative t. And so each step I'm going to go through and then sort of double check to make sure I did my signs right. So what do these mean? So let's look at all of these terms for a second, see if they make sense. So I have t cosine theta. It's positive, and it's contributing to my acceleration. It's the component of the tension force that's sort of pulling it forward. That makes sense. So this p cos theta, that's also a positive contribution to the acceleration. It's the component of the push force that's giving me an acceleration. So this comes from the frictional force. This is opposing the motion of my object. I also have this term here. So this is the vertical component of my pushing force. It contributes a term that's inhibiting me. It's essentially enhancing the friction and frictional force between the ground and the box. So this component from the push force is in fact hurting me. It's inhibiting the acceleration. It's sort of pushing down on the box harder, increasing the frictional component between the ground and the box. Now this component here is the vertical component of the tension force, a term that from the vertical component. So this is in fact helping me, and it's helping me because it's contributing to lifting the box, it contributes to sort of lifting the box. It's not lifting the box above the ground, but it's trying to, and that's lessening the frictional force between the box and the ground. And so that's helping me move the box forward. So all of these terms have physical meaning, and I can identify the physical meaning of all of these terms, and it makes sense mathematically how these terms are contributing to the acceleration. Now what I might do is clean this up a little bit. I have a tension. I might factor out of a tension here. So there's cosine theta plus mu sine theta. And I might add that to my pushing contact force, which has a cosine phi minus mu sine phi. And then I have a minus mu mg, and that's equal to mass times acceleration. And now my acceleration then is simply this whole term divided by both sides by mass, and so my acceleration is equal to this. And this may seem quite complicated, but as long as you go slowly and work out the details carefully and follow your forces and follow this procedure, all of it works out. And I can't overestimate how important it is to sort of take your time with signs, but also using the check, not just solve for it, but at each point check what you have to see that it makes sense and that you can understand the physical meaning behind the terms that you have in your expression. So we've now answered the first part of this problem. What is the acceleration? The second question was, is there a phi where Bob is simply not helping? And we had a clue to that, didn't we, when we were understanding the physical meaning of these terms. This right here was Bob's negative contribution to the task at hand. The vertical component of his force was contributing to increasing the friction. So right here is all of Bob's contribution. And this contribution is going to be positive, leading to increasing the acceleration, as long as this term, cosine phi, is greater than this term, mu sine phi. If this term becomes less than this term, then the magnitude of Bob's push force, the net result is negative, which would tend to decrease the acceleration of the object. So from this, we now answer part 2, which is cosine phi must be greater than mu sine phi, or in other words, mu must be less than cotangent of phi. Otherwise, Bob is, or this angle must be, the cotangent of this angle must be greater than mu. Otherwise, Bob is not helping, but he's hindering accelerating the box forward.